Hello and welcome to a short walk through a project we are building called 3D Visual Test. It lives inside the BlockView Universe repository, and it is the start of something quite ambitious. The aim is to let you see the geometry of space itself. This will take about 7 minutes. The full version of the tool is meant to be viewed in cross-eye stereo. That means you cross your eyes slightly so that the two side-by-side images merge into one, and a true three-dimensional scene appears. This recording is a flat presentation about the project, but the project itself is built for stereo viewing. Part 1, why we are doing this. Physics visualizations are usually flat diagrams. A black hole gets drawn as a circle. A worldline gets drawn as a curve. The bowling ball on the rubber sheet has been used in every popular science book for 60 years. None of these are what space actually looks like. Space is three-dimensional. Curvature in 3 dimensions is not a sheet that dips. It is a continuous deformation of the geometry itself. To see it, you need to see in 3 dimensions. In Phase 1, we built the BlockView Universe Visualizer. A single HTML file, 5 spacetime scenarios, Schwarzschild black holes, rotating Kerr black holes, expanding cosmology, Feynman path integrals and causal sets. All rendered in the browser, all without a build step, all viewable by anyone with a browser. Phase 1 was about correctness. The metrics are real. The geodesics are integrated faithfully. The foliations are the ones a textbook would name, but everything is rendered on a flat screen, looking at a 2-dimensional projection of a 3-dimensional object. What if the wireframe grid you see in the scene is not a decoration? What if it actually represents space itself? And what if you drop a mass into the scene and the grid deforms in real time according to the actual gravitational field of that mass? That is what 3D Visual Test is the start of. The mesh is the metric. Objects with mass deform it. You move the mass with your cursor, and you watch the deformation follow. Cross-eye stereo is not a gimmick here. It is essential. The whole point is to perceive a 3-dimensional deformation of a 3-dimensional structure. On a flat screen, the deformation collapses into a projection that your eye reads as a tilted plane, not as curvature. With proper stereo, your visual system reconstructs the actual 3D shape, and the curvature becomes obvious. We render the scene twice, once for each eye with a small horizontal offset. Cross your eyes so the 2 images merge in the middle, and the scene pops into depth. The current prototype already has the navigation working. There is a 3D cursor that you move with the mouse. Scroll the wheel to change its depth. Hold Control and drag to orbit the camera. Hold Shift and drag to pan. There is a wireframe volume grid filling the scene, 8 reference objects floating in it, and a panel of controls duplicated for both eyes so you can adjust the view in stereo. You can navigate the cursor to an object, see a blue halo appear when it is in range. Click to select, then drag it around in true 3D. The depth sense works. The interaction works. What is not yet there is the deformation. Part 2, why this matters. The physics underneath is not an analogy. It is general relativity. For a single non-rotating black hole, the spatial metric in isotropic coordinates has a simple form. There is a conformal factor, psi equal to 1 plus the mass divided by twice the radial distance. Every spatial measurement scales by psi to the 4th power. For multiple bodies, the factor superposes. Psi becomes 1 plus the sum over all bodies of their mass divided by twice the distance to each. That is called Brill-Lindquist initial data, and it is an exact solution to the constraint equations of general relativity for a moment when all the bodies are at rest. Computing psi at every vertex of the grid every frame is exactly what GPU vertex shaders exist to do. A few thousand vertices, a few dozen masses, executed in parallel. The cost per frame is trivial. The fragment shader can color the mesh by curvature intensity, giving you a heat map of where space is bending hardest. This means the CPU handles the orbital dynamics, and the GPU handles everything visual. Even with 100 bodies and 10,000 mesh vertices, the frame rate stays above 60. After single body deformation, we want orbital dynamics. Watch a planet bend space around a star while the planet itself orbits, then black hole binaries, then the merger phase. Eventually, the time dimension itself rendered as geometry rather than animation. And then, VR with haptic gloves, where you can reach out and feel the tidal forces near a black hole. Part 3, who else is doing this? We did a survey. The short answer is nobody is doing this exact combination. There are excellent single-body ray tracers on GPU, from research codes like G-Ray and Odyssey to browser DMOS. There are full numerical relativity codes that run on supercomputers and produce post-hoc movies. There is a sandbox in Babylon.js that lets you drop planets on a deformable grid, but with Newtonian physics, not actual general relativity. The closest neighbour is a project from the University of Illinois called POINT-VR. It is a MetaQuest app where you place masses on a deformable spatial grid. Same interaction model as ours, but the physics appears to be pedagogical rather than computing actual conformal factors. We could collaborate. They have the VR platform and the educational pipeline. We have the actual physics and the GPU shader architecture. The split is natural. If we get this working, it will be the first tool to combine actual general relativity, multiple bodies, a visible deformed mesh, real-time GPU rendering, stereo 3D, and live dynamics. The math is tractable. The hardware is here. The infrastructure is built. The next milestone is the vertex shader that does the deformation. Thank you for listening.